Hi, the topic of this video are non-asymptotic bounds for forward processes in denoising diffusions, and this is based on recent joint work with Alex Mijatovic. I will make two videos on this topic. In the first one, I will describe the setting and some key results, and in the second one, I will describe the generalization of those results and their proofs. Denoising diffusion probabilistic models are a recent advancement in generative modeling that led to state-of-the-art results across various domains. The aim of these models is to generate artificial data of a certain type. These models work by collecting a large data set of the type we want to sample, and then they corrupt the data set by running a forward diffusion process towards its structureless invariant measure. Stochastic differential equations can be reversed, so running a reverse process from the stationary measure of the forward process back allows the user to generate artificial data. This idea leads to an approximate algorithm for simulating the data distribution and generating artificial data, and because this is an approximate algorithm, it has various sources of error. The first source of error is connected to the forward process. In order to reach stationarity with a forward process, we would have to run it indefinitely, which is of course not feasible. So we stop it at some terminal time t. However, the marginal distribution of the forward process at some terminal time is not available. So the reverse process is initialized at the invariant measure of a forward process. And because this one is not reached by the process, this leads to the first type of error. The second error comes from the fact that in order to run a reverse process, we need information about the marginal Q of the forward process initialized at some unknown data distribution. And because this marginal is not explicitly given to us, it has to be learned and approximated using machine learning techniques called score matching. These are extremely computationally intensive techniques that make this whole algorithm work. And for us, the important thing is that the error that arises with this approximation increases in time. The third source of error simply comes from the fact that in order to sample a diffusion, we need Euler-type schemes for discretization, which leads to discretization error. And again, the important thing here for us is that this discretization error increases in time. So we have our algorithm, which has three main sources of error. The first one is connected with the choice of the forward process, and it decreases in time. And the second and the third one are the artifact of the method, and they increase in time. It's thus necessary to pick a forward diffusion process that converges to stationarity fast, as this allows us to choose a smaller time parameter, which in turn decreases the second and the third error. So naturally, we want to study convergence of various different forward diffusion processes initialized at relevant data distributions. In order to do that, we need to make some rigorous assumptions about the structure of the initial data distribution. Data distributions that appear in practice are known to be extremely high-dimensional and multi-modal. So we consider high-dimensional multi-modal distributions and we parametrize them with respect to the distance to their furthest mode, which is also known to grow in dimension. Such a distribution would then charge a certain amount of mass to this furthest mode and very little mass to the points further away than the furthest mode, which is natural because it's a furthest mode. So just for visualization, let's see a two-dimensional picture to see maybe how these high-dimensional distributions would look like. The distribution on the picture is clearly multimodal. It has some mode that's the furthest away from the origin, and it charges very little mass to the points which are even further away. Note that this is an extremely mild assumption, as we make no assumptions on moments, log-concavity, existence of density, or KL-divergence with respect to Gaussian, as you want to capture data distributions that actually appear in practice. And also the important fact is that this allows for a manifold hypothesis, which states that complex real-world data often resides on a submanifold of Euclidean space of possibly high codimension. Now that we have a rigorous assumption on the initial data distribution, we want to study convergence of different processes and initialize these distributions. And the canonical choice for the forward processing denoising diffusions in applications is the Ornstein-Uhlenbeck process, which is convenient because of its Gaussian invariant measure and exponential rate of convergence to stationarity. So naturally, we want to study the convergence of OU process initialized at the data distribution that satisfies our assumption. So we start with distribution with the furthest mode at the distance r from the origin, and then we see that if we pick a time horizon that's slightly less than the logarithm of r, the OU process will be far from converging. On the other hand, if we consider a time horizon marginally more than log of r, the OU process will converge, which leads to an interesting probabilistic phenomenon. If you fix the diameter of the furthest mode and the error tolerance you want to achieve, and then send the distance to this furthest mode to infinity, you see a cutoff-like phenomena for the convergence of the OU process. This was an interesting result for us, so we wanted to test it in practice. We simulated the OU process, initialized at different images, and then plotted the distance between the marginal and the Gaussian invariant measure of the OU process as a function of time. And we started with a low dimensional image of only 900, which is reasonably close to the origin, and the OU process is converging very fast and no cutoff is detected. On the other hand, when we simulate the OU process at an image which is high dimensional with the dimension more than 1,000,000 and further away from the origin, a cutoff-like behavior appears. So we have a long period where the process is far from stationarity, and then later on we see rapid convergence, which suggests that that the cutoff-like behavior does appear in practice. And it also opens up a relevant probabilistic question. Can replacing the OU process with an ergodic diffusion speed up the convergence in the presence of large R? And in other words, what do we mean by that? Can we get rid of this long period, or at least significantly shorter this long period, where the process is far from stationarity, by replacing the dynamics of the OU process with another different type of ergodic diffusion? And this question is also motivated by the following observation. Ornstein-Uhlenbeck process belongs to the family of Langevin diffusions, which are ergodic diffusions with additive noise. And it is known that Langevin diffusions do not converge, aren't the class of diffusions that converges to their invariant measures at the fastest rate. And let's see this with the following example. So if you consider Langevin diffusion with an invariant measure that has stretched exponential tails, so exponential minus norm of x to the p, where p is between 0 and 1, then the convergence to stationarity here is also stretched exponential, and the heavier the tail, the slower the convergence. On the other hand, there is a generalization of a Langevin class known as tempered Langevin diffusions. And if you pick in this class L equal to 0, you recover the classic Langevin class. But if you consider L to be greater than 0, then you obtain a diffusion that has the same invariant measure, but different dynamics with multiplicative noise. And the interesting bit for us is that if you consider multiplicative noise that grows sufficiently fast, then this slower stretched exponential convergence turns into an exponential convergence. So to the same invariant measure, the tempered Langevin diffusion with multiplicative noise converges exponentially when Langevin diffusion converges with stretched exponential parameter. And this opens a natural question. Can we replace the OU process with additive noise with another diffusion with multiplicative noise and initialize this process at the relevant data distribution? Could we get rid of this cutoff-like behavior where for a long time the process is far from stationarity? And this question is answered by our main result. We start by a class of tempered Langevin diffusions, which of course contain the OU process. We consider drifts that grow at most linearly. This is because diffusions with superlinear drifts are known to be difficult to sample from and therefore not useful for applications in this setting. Also, we fix the constant growth in this linear upper bound for the drift, and this is because while it is known that multiplying the drift with increasing the drift by a constant factor would increase the convergence, this would only happen because of the time change-like effect on the behavior of a process and would not improve the performance of the underlying algorithm. So it makes sense to also bound the constant in the growth of the drift and fix this family. The second assumption we make is on the invariant measure of y. We assume that this invariant measure is spherically symmetric, and the second technical assumption essentially states that it is sufficiently light. And this is because we want to extend the family of Gaussian invariant measures, but remain within the realm of invariant measures that can be very efficiently sampled and useful for applications. And then our result reads as follows. We start with invariant measure, which has the furthest mode at the distance r from the origin, and we choose a time horizon to be slightly less than log of r divided by mu. And then every tempered Langevin diffusion in this large class fails to converge. But if we consider a time horizon that's slightly longer than log of r divided by mu, then the OU process converges, which shows that in this setting, the OU process is hard to beat. We also proved a generalization of this result, which shows that the same conclusion holds when one replaces tempered Langevin diffusions with a far larger class of SDEs. And more details about this topic can be seen in the second video I made here. I'd like to conclude with some remarks. We showed that the OU process cannot be substantially improved within a large class of diffusions when initialized at relevant data distributions that satisfy the manifold hypothesis. Our theorem also suggests the correct terminal time horizon, which should be taken as a function of the furthest distance to the furthest mode from the origin and the desired error tolerance. The fact that the time horizon has unbounded growth in the distance to the furthest mode to the origin motivates the use of alternatives to diffusions in denoising diffusion modeling, such as Schrödinger bridges, which exactly interpolate between two distributions in finite time, regardless of how far apart their modes are. Another development that would aid this problem is efficient sampling of algorithms for uniformly ergodic diffusions, which is, to the best of our knowledge, not available in this setting. And lastly, we proved the cutoff behavior for the convergence of the OU process initialized at the data distribution. And a relevant question for us is, can we also establish the cutoff for the reverse process of the OU process? And can we prove this rigorously? And this is something we'd like to tackle in the future. Thank you for your attention. Here are some sources.